We have Monte from Splice Machine. He's the CEO of Splice Machine. We're going to talk about transactional RDBMS, HBase. Welcome, Monte.
Thank you very much. Appreciate you inviting us to speak tonight. Those are two great talks, really interesting. I think we fit in nicely in the flow. We're a little different than some of the database and data manipulations that you've heard, in the sense that we're really trying to be a general purpose database. In fact, in some cases, we're finding that we can replace Oracle and power applications in real time on the Hadoop stack. And I'll tell you some stories about that. And in some cases, we're finding a 10x price performance improvement. It's an affordable scale-out type of database, shared nothing architecture. It is completely ACID compliant, and it essentially allows you to use existing ANSI SQL to execute with very little rewrites. The best way to tell this story is in the context of what customers do with it. Our first customer that's been vocal had a real big problem with a packaged application. The customer was Hart Hanks. They're a direct marketing service, and they built a campaign management application from a number of components. They built it from Unica, which is now owned by IBM, standard campaign management application. They did their reporting on IBM's Cognos, and they manipulated data with the ETL system Magnetio. All of this was powered by Oracle RAC. And we met them about a year and a half ago, and they were out in market trying to figure out what to do because their Oracle implementation for this application was grinding to a halt. They weren't meeting SLAs. They were at risk of losing customers, and they were looking at a variety of different solutions, from looking at other database platforms, as well as just perhaps writing NoSQL or replacing the whole stack. So we said that we were trying to build a database that could replace Oracle, and they engaged us and said, well, let's prove it. Gave us a bunch of queries that were giving them a whole hell of a hard time, and they had been performance tuning these queries on RAC. There was a tremendous amount of partitioning logic and other stuff in there that we stripped out. We just ran this on our platform, and we were basically able, on a set of queries, like 5 queries, getting 3 to 7 times faster on a platform that would be 1/4 the cost. And we were lucky enough to get them as a customer, and they're now replacing this entire layer, keeping the entire application layer and throwing out Oracle RAC and putting Splice Machine in. And so it's our best win to date as an example and a story. Other kinds of applications that we see out there are people just like the Unica example, simply wanting to power real-time concurrent applications. And others are trying to use us in operational data lakes, where it's really important to change individual records rather than doing big batch appends or batch updates. So I think that probably the best way to characterize this is tell you how it's built, and maybe give you a feel for what we think we do well. I imagine if I were to do a quick survey out there, how many of you are Hive users out there? Quite a bit. How many of you are Spark users? A couple. Any Tez users? A couple there, but a lot of, obviously, Hadoop MapReduce programmers out there, right? Is everybody a Hadoop person for the most part? Obviously, you would be here if you weren't interested in Hadoop, but I imagine all of you have written MapReduce programs. So our purpose in life is to be able to do the kinds of things that a traditional database would do for OLTP applications. And what does that mean? Well, all of those other SQL on Hadoop systems, from Impala all the way through to Hive, they're basically very good at analytical computations. They're very good at long-running queries. They're very good at big table scans and large aggregations, typically when you have to touch every record. But what happens when you want to find one particular record? Or you have to do millions of updates in a very short period of time, not just appends, but updates or deletes. What if you have to do small range scans? And what if you have to manage concurrency, where you have many connections to the database doing reads and writes at the same time, and you need to keep that database consistent? Those are the features where Splice Machine would fit well versus some of the other SQL on Hadoop out there. The way we built it is in the following architecture. We came to market quickly because we started with some open source components. We took Apache Derby, which is a fairly old relational database system. I'll talk about it in a second. It's ANSI-99 central file-based system, and we essentially connected it with HBase. We take advantage of the Derby parser, its planner, a bit of its optimizer, and a bit of its executor, and we replace its storage layer. And I'll talk more about this in a minute as we go a little deeper. So that's Derby. Derby's a 100% Java relational database. It started in 1996 as Cloudscape was acquired by Informix, and then IBM acquired Informix, and IBM contributed the code to Apache back in 2004. It has many of the flavors of DB2. It has many companies' approval out there. It typically uses an embedded database out there, and it's a real database. It is able to do stored procedures. It has triggers. It has isolation support. It was a pretty interesting piece of software out there. But the problem with it is it's centralized. And I guess what we do here is, if you were to take a look at how we work and how we process SQL, we take a prepared statement. We look to see if it's been processed before, if it's in cache. We parse it using Derby. Derby creates a plan. That plan gets compiled into bytecode, and that bytecode instance is distributed to a bunch of servers. And I'll give you a view of that here. Basically, what happens is that when you compile the SQL bytecode, it gets serialized to each HBase node in our implementation. And it is executed locally on that HBase node utilizing HBase's coprocessors. How many people in here know what an HBase coprocessor is? A couple. Let me give a quick backgrounder on that one. It's a new feature that was added fairly recently to HBase. It's essentially the same as a traditional database's use of triggers and stored procedures. There are endpoint coprocessors that let you run a bit of custom code on every HBase node in the same memory space as the HBase local data, getting access locally to the data on a particular region server. And then there are something called observer coprocessors, which are essentially little pieces of code that you attach to the database mutation operators or access operators. So on every get you run something, or every put, or every delete, or every scan. So you can attach your own custom code in there. This allowed us to essentially execute full-up SQL processing utilizing HBase and pushing computation down close to the HBase node. So essentially here what happens is you connect to any one of the HBase nodes that is also a SQL client. You enter in a prepared statement. You connect to the database and process a prepared statement. It compiles the plan. The plan gets compiled into bytecode. The bytecode is then sent to each one of these particular HBase nodes, and each one executes in parallel its code, and then of course the results get spliced back together again in the execution of the SQL code, hence the name of our company, Splice Machine, and that's essentially how it executes a SQL plan. So within our architecture, essentially there's no MapReduce, and there's no essential computation that's being done at the high level. It's all being done local where the HBase node is. Essentially, we've done a few things to Derby in order to accomplish this. So first, Derby had a very flexible and modular storage component. The storage module can be ripped out. That's exactly what we did. It used a block-based B tree type system, and we ripped that out and put HBase in. It used concurrency in a very old way using arrays and locks, traditional lock-based concurrency. We implemented an MVCC, a multi-value concurrency control method, which is traditional snapshot isolation. I'll talk about that in a minute, in order to get full of ACID compliance on the database. It also had a few join algorithms. We replaced the join algorithms with distributed join algorithms. Right now, we have a distributed broadcast join, we have a sort merge, a merge, and a number of other approaches, as well as just natural joins and what you would classically have to do for Cartesian product type of operations. And we built a nice resource management component over this system that essentially takes tasks that are being distributed to each HBase node and manages the computational resources of those nodes so that you don't hit deadlocks and you can control what tasks are being used. So that's essentially some of the architecture. We've done some interesting things inside of our system. One, we don't do a straightforward encoding of a SQL table in HBase. In other words, if you have 5 columns in your SQL table, we don't have 5 columns in an HBase table due to the bloating that happens the way that HBase represents things. We do a very compact encoding, and we have only 1 column for data and 1 column used for transactional information. And we compact all data into that efficient representation. It's a sparse representation. You don't have to represent every column if there aren't any values for every column, but it is a compact representation. And the reason why we did that was because when we didn't do that in our first version, we found that somebody's 10 terabyte database would turn into a 50 terabytes of storage based on HBase's inefficiency and how it represents data with indexes, as well as the, of course, replication factor on Hadoop. So by doing this very compact encoding, we're able to maintain a 10 terabyte database that's maybe on Oracle. If it's migrated over to Splice machine, it's roughly the same size. We do have full SQL 99 coverage. We also did some extensions with some window functions. Our early customers needed some window functions. We don't do all of 2003 window functions, but we do some of the important ones now. Like I mentioned, we do lockless ACID transactions. So the way this works is very straightforward. For those of you who don't know what snapshot isolation is, essentially any mutator of the database is given a timestamp, and you open up that transaction for that timestamp. You can make any changes you'd like to the database. No readers will be able to see those changes until that transaction is committed. And in order to create consensus of what is the current timestamp, we use Zookeeper as a consensus manager, as that's a standard component for the HBase system. This research extends some of the work that Google did with Percolator, also some of the work done on Amit at Yahoo Labs, and some of the work that was done on a PhD thesis at the University of Waterloo. Essentially, the cool thing about this is that it adds multi-row, multi-table transactional capabilities to HBase. And it has a full commit rollback system, so no matter how many updates are being made, that those updates can be rolled back on the system. It also is pretty cool. It operates on indexes at the same time as data, so that if you're updating data the indexes for that data, including secondary indexes, are maintained within transactional integrity. So if you did commit your data updates, the indexes would be also committed and updated. If you rolled back, they would both be kept consistent. We're just a standard ODBC, JDBC database leveraging some of the Derby components, so any customer would be able to use their front-end BI tools with us. We look SQL 99 to anybody. And if you think about the SQL database ecosystem and where things lie out there, we are best utilized in circumstances where there's substantial concurrency, where people need to read and write at the same time, where you need to access small numbers of records very, very quickly, and to be able to do this all with transactional integrity. If you look at the world, we kind of see the world like this, although the world's blurring these days. Essentially, there's SQL on Hadoop, which is very analytically oriented, and there's MPP, which is very analytically oriented. And then there's some of the new SQL stuff that's going on. And some of the new SQL stuff that you hear about is in-memory, big analytics type of workloads, kind of like what MySQL does. And some of the new SQL is really trying to be transactional, perhaps like new ODB. I think we're more in that world, but we do benefit from being on the Hadoop stack. We think we're the only transactional Hadoop relational database management system out there. And we're building a number of the components that you might expect that an OLTP system requires, like backup and restore, replication techniques, and explain facilities, and management consoles, and all of the things that you typically need to run a mission-critical application. So our goal is really to take Hadoop into a new class of workload, whereas it's been extremely well deployed for building models and doing a great deal of analytics, a lot of batch data manipulation, data transfers, ETL, but it hasn't really been used, other than with some raw HBase implementations, that hasn't really been used as a mechanism to power real-time applications, and we're hoping to change that. And we think that there's a grand opportunity out there because people just really are tired of their legacy relational database management systems, either because they don't perform or because they cost so much money. And we're hoping to take advantage of that. So a lot of people are excited about what we're trying to do out there. It's early days for us, version 1.0, about 50 people in the company and just a few customers out there. And so we're really at our early stages, but that's basically what our mission is out there. So I tried to keep it fairly high level, architectural about what we're doing, but happy to take questions from the audience about it. Yes?
Okay, so what do you do about the PLSQL side?
What do we do about what? Can you repeat that again?
So regarding the Oracle compatibility, what did you do SQL, what about PLSQL?
Yeah, so Hardhanks, for example, had thousands of PL/SQL procedures coming out of that. And when at first we thought this was going to be hellish for us. But it turns out there were a number of PL/SQL translation and compilation tools out there. And what we literally did is take their PL/SQL, put it through a compiler, and generated our own Java-based stored procedures. We have a full stored procedure capability, but of course, it's a different syntax than PL/SQL. So any implementation that's heavy in PL/SQL will require that stage of migration, and it's work, but it's not months upon months of work. It's weeks of work, and it's been affordable for the clients that have done that with us. Yes, in the back.
Just curiosity, why you choose Derby, not MySQL, not Postgres? What's the story behind it?
Yeah, so the question is, why did we choose Derby and not Postgres or MySQL? And the answer is, the simple answer is that we wanted to stay within the Java environment. Hadoop was Java, HBase was Java. We just thought it would be more efficient for us, probably not efficient for the code, but more efficient for us if we stayed within one programming language environment. I think that was a good decision across many different dimensions. But of course, we hit some of the same kinds of performance challenges that you heard about in previous talks, even tonight. We have to manage our heap very, very carefully. And we have to be very careful about garbage creation, the garbage collector. We have to tune garbage collectors. And being a Java-based relational database has its challenges, but we did it for Java. There was a question about there.
Yes, it's me again. I saw on one slide it said does not store nulls. Can you go into that in more depth and what it means from a data quality standpoint?
Sure. What I meant by the it does not store nulls, in that compact encoding that we talked about. Say you had a table that had 500 columns in it. Sometimes when we say to customers we make one column of data, they think, oh my God, if I had 500 columns and 400 of them were nulls, this is going to be such wasted storage. And all we mean there is that our encoding doesn't make you have 400 explicit nulls in there. We have delimiters that can indicate exactly what fields, what columns are in the encoding. So it's just an efficient encoding is what we meant there. Yes?
So do you use bulk loaders, or what's the mechanism to load the data?
Great. So loading the data, we put a lot of, the question is what do we do for loading the data? And this became incredibly important to us because our customers were giving us terabytes and terabytes of data, wanting to do a POC with us, and it was taking a whole hell of a long time to get that data into our system. So what we did is write a parallel batch write pipeline. And what that means is we take, let's say, a huge HDFS file, and we batch it into batches, and we push it out to each HBase node, and each HBase node can then process the ingestion with pure transactional integrity to get parallel ingestion. So we built our own batch import mechanism in order to get the maximal performance as we can. And I think we'll be putting out metrics of this. Our objective is to easily be able to do millions of records a second. The question is how many nodes you need to do that, and we're doing those benchmarks now that we'll publish in our next release. Yes. Oh, I think the mic is over there. Sorry.
Yeah. So I got a couple of questions. One is, do you know about Trapodium, this SQL on Hadoop implementation that's in progress, released by HBase? That's one. And
Yes.
do you have any performance metrics for this one versus current Stitcher initiatives and other things?
Yes, great question. So the first question about Trafodium, we do know about Trafodium. We think it's great that there are other people out there trying to make a real-time transactional Hadoop-based system. Although I don't personally know a lot about that architecture, but my architects tell me that it's based on some very antiquated concurrency models that are somewhat lock-oriented and not a snapshot isolation, and therefore would not be able to power real-time concurrent applications the way we would. I don't know if that's really true, but that's what I'm told. I haven't used it. I'd love to learn more about it. But that's, I think, our current take on that. I'd love to learn more about that. The second question is, what benchmarks do we have out there comparatively to other SQL systems? We're just getting underway on our benchmarking competitively, as well as through TPCC and TPCH. We think we're going to be the only vendor that can run TPCC on Hadoop. And we're putting those numbers together now, and essentially my team has certain objectives as to what our TPCC and TPCH metrics are going to be, and we're tuning to that right now, and I expect those metrics to be out within a couple of months max. But I don't have great numbers yet to compare, but I do know that we're a hell of a lot faster than Oracle out there on a much cheaper platform for most things. One place that we're not faster than Oracle on yet is on the native OCI client that Oracle has to bring data in and out. Our ODBC connectors are slower, but that's something that we'll quickly remedy. So stay tuned for benchmarks and comparisons from us. But we think we can crush anybody on the fast lookups, range scans, and updates, TPCC types of operations. I think that others will be faster than us on TPCH types of benchmarks that are full table scans. But in the use cases we're targeting, I think our TPCH and full table scan type of analytical operations will be totally good enough for those use cases, but will be slower than I suspect something like an Impala if we were running a huge model and a TPCH type of aggregation or join against that. I don't know, but we'll put out those numbers. We'll find that out. You asked one, so let me get a new one and I'll get back to you. Yes.
So I want to follow up on that. So
Okay. He's got the mic, he's got power.
Is it possible to partition your workload in such a way that you do part of the work on Splice machine and part of your work on other?
Yeah, it's a great question. The answer is absolutely yes. We're H-catalog enabled. We're doing lots of things with Spark, where some is on Spark and some is on us or some other platform. We're even in our lab prototyping some of our internal join and computation engines actually operating on Spark, which will have a completely different OLAP profile. That's a future from us. But to answer your question succinctly, you can do some work outside our system, some work in the system. The compiler we just heard about that sits over lots of systems really intrigued me from that perspective. I think I need to learn a lot more about that's going on. But you certainly can push analytical operations that may be better on a columnar representation or on some other MPP box into that world and join it with us. So that's totally feasible. Okay.
Good question here. Okay, so comparing relational database with HBase, now I think a primary key will equate to your row key, right?
Right, so we use HBase's primary keys as our primary keys. We leverage that mechanism, that's correct.
Right. So since HBase does not support secondary indexes,
Right.
how have you implemented that?
We implemented secondary indexes as dense indexes as additional HBase tables.
Okay, so kind of like an alternate key?
Yeah. And we have our optimizer smart enough to pick the index in the join algorithm so that we get the efficiency of that secondary index inside the joins.
I have
Yes?
a follow-up question on this. So, what if the data table in the HBase got compact or split? So how do you handle the index?
Excellent. So I think the question was, and not everyone might have heard it, how do we handle splitting and compacting in HBase when we're utilizing secondary indexes and doing our operations in general? This is probably the most significant amount of innovation we had in our development, because as we're executing the SQL plan and our tasks are taken off the queue and start operating, at any particular point, HBase right out from underneath us might split a table, right? And it might trigger a compaction. So we have many mechanisms within our task execution structure that can recognize these conditions. Perhaps some of them are timeouts, perhaps some of them actually explicitly know what's going on, and that can trigger retries so that when the H files are quiesced and the system's ready to be processed again and the region is available, it just kicks in again. And let me mention also that different than some of the other architectures out there, like Impala, a long-running join in many of the architectures out there, if a node goes down, that actually kills the whole query. But we have a very resilient mechanism. If a node goes down in the middle of a query and the region comes up on another region server, our joins and long-running queries will just simply continue on that other platform. Now, resilient, we do materialize some of our intermediate results on HBase, which has a performance impact, but gives us this availability and essentially this resiliency. Yes?
Okay, I have two questions. First is how do you handle a conflict when you have a multiple transaction? The second one actually relates to compaction. So you have transaction, how about you do the undo? Like the underneath file system has been doing compaction, and those data has been moved around with a different region, and you need to undo. How do you do those? How do you recognize those?
Okay, so let's see, the first question, what was the first question?
Conflicts.
Conflicts, right. So in snapshot isolation, you have no read conflicts you have to worry about. Reads are not locked, they can just do whatever they want, they don't have to worry about anything because they're only reading in the timestamp that, any timestamp younger than basically later than that. Now, writes have to detect write-write conflicts. So we utilize these observer coprocessors in HBase to essentially on any write be able to introspect any transaction state. And if you're trying to write to a record with a timestamp that is essentially writing over a record that is in transition, its state transition and the transactional state diagram is not committed or rolled back yet, then we can detect a write-write conflict, in which case we simply fail. Right now it's optimistic, I think it's called, so that the first transaction is going to get control and the second transaction will fail. Now, the second question has to do with compaction. Compaction really doesn't impact us at all, I mean, other than from a performance perspective. And the reason for that is that every data value in HBase in general has a timestamp associated with it. We leverage those timestamps. So those follow wherever the files go. Compaction is really, just a function of taking two smaller H files and basically putting them together. And the timestamps will be preserved and the transactional integrity is preserved. It's just physically changing its place. HBase will still be able to find it just like it did in the two H files, just more efficiently. Did that answer your question? Yes, another question.
That is my turn.
It is.
So, do you do anything with JSON? Because the HBase can store the JSON, not the question is before the processing.
It's a great question. Do we do anything with JSON? We have customers that will store JSON in, varchars or some other representation. But my goal is to actually extend our SQL processing with a JSON query extension, so you can do some wildcarding with dot notation. We're not there yet. It's not in our current version. It's in our roadmap. We'll get there, but I suspect that will make us, very attractive to those that may have been enamored with the ease of use of a MongoDB, but maybe been disappointed by its scalability. I think that's a market that's ripe for taking, and we'll hopefully be able to do that in the coming year or so. But right now we're very focused on traditional SQL applications and powering those, but we will extend to support JSON as a first-class data type in our system. The neat thing is that Derby already parses XML, so we're pretty close to being able to do things like that and has some extensions in there, and we'll probably leverage some of that, but we're not there yet.
That was the SQL JSON standard, which is
Right.
different from Derby.
Yeah, we might just adopt that. Yes,
How are you handling query queuing?
query queuing?
Yeah, queuing up various queries from all these different applications.
Right, so essentially, we have a task scheduler within our system. Every time a SQL statement is executed, that bytecode is executed, that actually turns into tasks, and the tasks are in queued, and those queues have priorities, and we just execute through those queues. It's a fairly simple mechanism. In the future, we will let that queue logic actually reason about the user group and roles attached to the tasks, so that IT can manage their workloads and not let a weekly report or an ad hoc report written by an intern interfere with OLTP queries and things like that. Right now, it's very simplistic. It doesn't do user group role sort of priority queuing.
So
Yes.
you consider something like looking at name node and actually looking at the data and becoming sensitive to where the data is to send the queries out to just the applicable data points.
Well, right now, okay, so now I see your question about the name node and looking at where the data is. So,
Right, you could be massively parallel in your queries, right?
right now, the way we work is, since we're based on HBase's data representation, it is automatically auto-sharding the data across every node, right? Every region server at least. So the computations take place on every node that if it's a table type of computation. Alternatively, if it's, for example, a very specific operation on a filtered set of records, HBase is going to be smart to only execute that task on the nodes within your range of your indexes that you're working on there. So it introspects based on knowing how the data is sharded already. Now, an important future for us is getting really smart about assignment. HBase's assignment algorithms are fairly simplistic. I think there's a lot of research that we can do in making that smart and making the sharding algorithms based on introspecting the SQL that's going to run, and being smart about how to distribute the data to make sure that if you're doing certain joins and you may or may not have indexes on those join columns, are essentially partitioned in a ways to ensure locality. We're not doing that fanciness yet, but that's a future as well. Any other questions? Thanks, this was fun. I appreciate all the questions.
Thank you so much.